Hi everyone, we're Team ParaDocs and thank you so much for joining us for our fall validation demo today. Our team is Param, Shiva, me, Live, Kimi, and Abhishek, and we're sponsored by Smith and Nephew with our wonderful mentors Ranko, Parker, Kaushik, and Sundaram. And we're joined today by our patient Skelly, who presented to the OR complaining of severe pain in his left knee. So the doctor ordered an X-ray and noticed that Skelly's left knee has no cartilage in it anymore. So this is a condition known as osteoarthritis, where as compared to a normal knee, there is wear and tear of the cartilage that is present between the femur and the tibia. Osteoarthritis actually leads to about 800,000 surgeries of total knee replacement in the US alone annually. And unfortunately, Kelly is also going to be a victim of total knee replacement today. In this surgery, the damaged part of the tibia and femur is replaced by an implant. And to do this, there are slices that are made on the femur and the tibia so that the implant can snugly rest on it, hammered in. To make these cuts accurately, surgeons use something known as a surgical guide, which is drilled into the bone with these surgical pins. Here. Sorry. Yeah. So this surgical guide is drilled into place with these surgical pins that are slid into the bone like this. So the objective of our surgery today is to actually drill this autonomously. So what we see is being done by a surgeon over here will be done by our robot. This obviously is not the entire surgery because that is not our intent. We are not replacing surgeons here. We are working with them to assist them in certain parts of total knee replacement. This brings us to our solution, an autonomous, non-invasive, and robust robotic assistant for total knee replacement. What do these terms mean? Autonomous. So our system, right from planning to registration to manipulation to drilling, is done entirely autonomously with no input from us. We can take a surgeon's input for improving accuracy, but it is just an add-on. Secondly, we're non-invasive. So traditionally, in total knee replacement, these IR trackers are drilled into the patient's bones, and that is how you use a camera to figure out where the knee is located and where the cuts are being made. But this is a very invasive procedure, and in our surgery, we've made these disappear, and we are going to instead be using an RGPD depth cam, a simple real sense depth cam, to get the same accuracy and to figure out how our tracking and registration is working. Finally, we're robust. So, surgical wards aren't the most predictable environments, and there's always a chance that there'll be some movement in the patient's bone or a need to stop the surgery in case of an emergency arising, in which case we have to account for all of these while making a robust design. This is our setup where we have a KUKA LVR Med 7 on which is mounted Intel RealSense D405 right there on the end effector and a Dremel 9100 which has been electronically interfaced to get automated autonomously. Or not. Unfortunately, last night we lost our Dremel 9100 and we had to replace it with a Dremel 4000 that you see here. The process.
All right, coming to the process itself of what we're about to do. Well, the first thing is the plan. What we mean by the plan is that the plan is a static post that is defined with respect to a 3D scan that we have of the femur. The main idea being if we localize this where this thing actually exists in world space, we know where the goal is supposed to be. Second is registration. So it tries to answer the question, where is the femur here? Or well, better yet, where is the femur here? Because this is the actual point cloud that the camera of the manipulator sees. Well, it's right here. This job is done by a computer vision and perception pipeline to localize the scan of the femur. And once we have that, we know where to drill. And we simply drill. But if you are familiar with our project or if you have seen our spring demonstration, there's nothing new, right? And you would be completely justified to ask this question. Well, I would point you to three things. First is the search line. So basically, when we register, we usually need an initial estimate or a guess. And you can implement custom models of fancy heuristics, or you can simply ask the expert who's right there. So we ask the surgeon to annotate a single point on the femur and the tibia, respectively. This makes the system more robust, and it's also a much more intuitive interface for the surgeon to use. Secondly, we now have a tracking system in place. That means once the points are annotated, the points are constantly tracked, so we can always re-register without user intervention, and this also aids us in motion compensation. And finally, we have developed a new system called Parasite. The key thing about it is that the central node for the host, which synchronizes between our tracking, registration, user interface, and all the manipulated stuff. But we're here to answer one final question, that is, did we do it right?
So in this surgery, how do we quantify how well we did? That brings us to our accuracy measurement, that we are trying to target an accuracy of less than 2 millimeters from what the surgeon wants to drill at. For having our accuracy measured to be 2 millimeters, we want the center of the hole we drill to be within a radius of 2 millimeters from the desired point. But if that's the case, and to measure this accuracy, we're going to be having this stencil placed on top of the bone, and our hole should lie within it. But if the accuracy is 2 millimeters, why does this hole look much larger than 2 millimeters? So we don't want the entirety of the hole to be within 2 millimeters, just the center of the hole. So if we account for how wide our hole is, which is on average about 4.4 millimeters, we take an offset of that from the radius of 2 millimeters to get a final radius of 4.2 millimeters, within which the entire hole must lie to achieve an accuracy of 2 millimeters. Let's go and see our demo in action.
Okay, so coming to the demo. What are we looking at here? This is our setup. We have a manipulator, end effector, camera all mounted here. We have our bones in the workspace in a location that can be seen with the camera, of course. And bring your attention to this screen here. What do we have here? This right side is the camera feed and the entire, well, point cloud and 3D space. This is what you can see from this camera right here. These are the buttons that, well, a physician can, or in this case, we can use to interact with the data system. And this one, I'll get to in a minute. So for the first run, we are not going to be adding any variables. Very similar to last time. We start, drill, just get our accuracy right. So coming to the workflow, as Abhishek told initially, that we ask the expert to annotate points. So when I start the system, I'm prompted to give it an estimate of what the femur is, what the tibia is. And well, once I do that, now look at this image here. What this is our tracker's output. The points over here, it says for one the femur tibia, when it's green, it means, well, the bone's stable. If it's red, it's not visible. And if the bones are moving, your points are yellow in nature. And the whole idea is that when it's moving, we want to, well, recalculate our results. We re-register as the manipulator moves, so that we know, well, hey, it moved. Now where is the final location? So let's start. So I just asked the manipulator to, well, track what the goals are. We can, well, give it a location. Well, I'm not supposed to do it in this demo, but well, oops. But yeah, sure. Now, what is the workflow from this point? After SVD, we were given the feedback that physicians like to be involved in the process. Even if it is just a little button to go boop and move it ever so slightly, just to be a part of what the entire process is. So we have a re-register option, which, well, the system automatically registers, but if you feel like the result is not nice and you want it to try again, you ask it to re-register. So well, you can see the result here. It's kind of pretty good, but just for fun, I'm going to re-register. It, well, didn't move because that's the best it can do. But yeah, let's actually get it to drill. Leave A stops.
Yep.
Yep. Cool. And let's go. Um, okay. You can come closer, have a look.
We can check the accuracy. Yeah.
Yeah. So before the demo, we had marked the point and drawn a circle in pencil. As you can see, it's right there. Let's start right here. Okay, please start. And as you can see, it aligns perfectly with our stencil.
Yeah.
To basically reference, you have to have a look. Yep. So this is what first demo. And of course, why is the hole this big? Is because this is a surgical pin. It's the same diameter for this because we wanted to be able to slide in and hook on. So that is the reason we chose this drill bit. That is why it is of this width, and that is why, we have these values. But this, we were able to get an accuracy of 2 millimeters. This setup is a RealSense camera with a Dremel mounted on a 3D printed end effector. All of you have worked with any one of you, whoever has worked with RealSense knows that we are at the absolute freaking limits of what this sensor can actually do. And on that note of pushing limits, let's talk about motion compensation. And Shivangi will tell us why.
So what we just saw was a static demo where we registered once, it went, it drilled, it did a good job, we got a 2 millimeter accuracy. But we also want to show that our system is robust to any motion that may arise. But this is a surgery. The patient is under anesthesia. They're bolted to the bed. Why would there be any need for motion compensation? So what actually happens in knee replacement is that our ankle is bolted to the table like so, but the knee is in free motion because the surgeon in the middle of the surgery might want to check the flexion of the knee and move it around to show that the implant has actually been placed correctly. Which is why we need to have the option to compensate for any motion that may happen in the knee while drilling or while generally in the process of the surgery. So let's start a second demo.
Okay, so second demo, basically the same workflow. I say start, I annotate my 2 points, and have it track. Now let's actually play around with this tracker. So we needed to be able to compensate for motion as we move, right? And we can go around and like front or quite literally go all around the workspace. Unfortunately, you do need to be in the frame of the camera, else it goes out. Like if you see here, the tracker can no longer detect it. It's out. Like, okay, fine. We're not gonna try to chase it or go in any unsafe positions. Once you're back in the camera's view, it can pick up, it can detect those points again, and then you're back in action. Okay. Yeah. And yeah, so as she said, the motions that normally exist in this procedure, things like a physician checking flexion, or the bone moving side to side. we could do it a little faster, but it would jerk. And just for safety reasons, we aren't making it do it faster because we want to be in control of where the manipulator is going. But
I have a question on that one.
Absolutely.
When it goes from side to side or when you rotate the phone,
Mhm.
do you not want to have a change in the angle of the drill as well?
So right now, because we're not tracking a pre-drill pose, we're tracking a hover pose.
Okay.
Just for
But at the end, it will
Yeah.
get into the proper angle.
yep,
Yes.
absolutely. Yes.
Also, the key thing to mention is while it's tracking, each time you move it slightly, it registers. So compared to the first semester where we just you press once, you register for 5 to 10 seconds,
Yeah.
the registration is real time.
Like if you notice, after all those motions, the registration is still perfectly aligned. But yeah, while you're still here, just look at the noise in this cloud. That's just the sensor noise that just exists with these cameras. But yeah, no, I mean, the question exists that, well, hey, we moved it around. I added all these variability in the system. Can it still drill accurately? Let's do a run, leave it, he starts. It's pretty well registered, but I'm just gonna click re-register just for the sake of it. And you can hear.
You guys can also look at the camera at the top left to see.
Here you can see the hole with the circle as it's heading back. Okay.
What happens if it's motion during the drilling process?
So there is a period that because if the drill is inside the bone, it doesn't make sense for us to move it because then it'll just damage it. So we have a certain locking period. So once you press drill, everything just stops up. Like we don't update the registration pattern, nothing.
The theory is that at that pre-hover pose that we're tracking, we are going to stay there until the bone is stable. The whole idea is when, if let's say the physician holding the bone has moved it,
Not going
Yeah.
on stable. Broad.
Yeah. and the idea is that it's fairly close enough to the bone, so it's a decent assumption to make.
Yep.
Yeah, you
Wait
can
for the
come
locking.
and have a look.
You want to check the accuracy again?
It's basically right there.
Like
And
that.
it's right there on the previous hole, so.
Same hole.
Yeah, exactly.
Was it a different one? It's the same one. It's basically the same.
Even after we did all this variability while registration, it was able to still find a hole and do it again.
The building's gonna be good.
We can
Yeah.
do it for 3 times.
We can.
Well,
We have that.
well,
Well, that'd be the right case, is maybe we have time to go down, but that was.
We can show one more thing, maybe the quick thing.
yeah, so another feature of the system that, well, I'd like to highlight is, well, let's say you're not happy with this hole. You want it to be like deeper or, well, just want to do it again, just for laughs and giggles. Well, let's say it's not deep enough and you're not satisfied and you want to repeat it. And I just say, well, go ahead and drill. And maybe midway you realize.
Yeah. The new drill, right? Yeah. Essentially, so that. Oh, you should first. annotate.
be ready.
Yeah.
Yeah.
Yeah, you first annotate.
We're just resetting the system back to start. It got stuck in the state.
Right.
Okay, it'll work. Yeah.
Well, the phone's not in the frame of the camera after all the motion. It returned back to home, so. It didn't know what it.
You don't close it, just annotate it.
Or-
You can drill, yeah.
Yeah, while you're drilling, at some point, to repeat this test, while you're drilling, at some point you realize, maybe you realize that it's wrong knee. You can, well, there's a feature to, well, stop it and, well, it'll stop right there, go back home, no harm done.
So what made it for board here? I'm
Oh,
sorry.
I clicked the mouse.
Oh, yeah. So we have a software stock. And ideally for surgeon has a pad tracker there, which we've noticed is there with a nephew. Suppose accidentally is going to the wrong knee to drill, the surgeon will quickly press, which is what we did with the mouse, a software stock itself, without shutting down the entire system with the stock.
This button here.
And then you just click on drill again and it will go to the right knee, hopefully.
The state of the motion stays the same, but yeah, let's just continue.
Yeah.
And this could be our repeatability.
There was 1 second.
Okay, sorry.
About the angular error, are you guys measuring that?
Oh, so we could actually just.
Rotation also, yeah.
So, we tended to measure the orientation by having a frustum like thing like this, through which the surgical pin should be fitting. But so
Okay, so
we can do it. Yeah.
So it's a very binary thing, the main thing is, in the sense, if the hole is perfectly in the center, it's a good measurement of orientation, but if it's on the side of the circle, it's not actually measuring the precision to it. Yes, yeah. But still gives you sort of a good idea of where it is. You can put the surgical guide pin also if you want.
If
Yeah,
you
yeah,
send
so-
the phone downwards, it will be a 2-degree
Yeah.
radius that we have.
So.
Because that's one of your methods.
So.
Yes, that is.
Yeah, absolutely.
Yeah, yeah. That's the idea.
So it's how much this rotates and.
Yeah, so that's the idea of, well, it's a binary. Yes or no.
Yeah. And this, this mark.
These were, yeah, the
Yeah.
other holes in case we decided to go there. But Branko, what do you have? Like, to have it? So that is what we had in mind, like, if it were.
2 millimeters and 2 degrees.
Yeah, so the orientation was off, that's what we-
So of course, Branko will be able to comment on this. But I think the industry is 1 and 1 degree,
The best.
Yeah.
and for scope of project, likely.
So we extremely accurate, and it is very difficult to replicate that with just a $200 camera that you can mount on an intersector.
That's right.
Yeah, even getting 2 millimeters and 2 degrees is a very big stretch goal, and we're very glad we did it.
Can we,
You
I mean-
clear?
well, this is it, we got 8 minutes left, I guess.
Yep.
So, I mean, we could try a few more drilling and holes unless that's gonna waste all of the spare bones.
Oh, we can use the same bone,
Or just say, well, we
Yeah.
have a couple of locations.
Yeah, you can actually play around.
We could do that, yeah.
you wanna, I think we need to change the location where we want to drill.
Oh, yeah.
But,
Yeah.
I think within 8 minutes, that might be a little bit of a challenge.
We can do that, yeah.
We can do that. So, do you want to do another repeatability?
We can flip it actually, yeah.
Oh, yeah.
Sure,
Do you
yeah.
want to flip one?
Okay, so let's just do one flip, repeatability, and then while you modify the hip hole too. So then we can change the location.
Okay, so we're changing the location. So we're doing a test of our entire limits by flipping the orientation and changing the location that we want to drill as well. And within that also you're free to like move it around and see the visual survey happening with it. So that would be like all our possibilities.
So for visual prevention, all the drilling is done with the
Yes, at this point, we're not doing registration of the figure. We may attempt to do it dividing like our encore arises, that is one challenge we have, but we had deprioritized the figure a couple of weeks into the semester. Because we needed some STL files to actually do the registration match, which we didn't get yet, so it got deprioritized.
Flipping it?
Okay, so.
We know it is definitely doable once we get the STL. It's exactly the same procedure.
Okay, do you all want to just do new hole here or same hole again?
New,
New hole? Okay.
how much time does it take to get a new? Okay, so we're drilling a new one.
So we have 3 spots on those locations, actually. Okay, usually we stand the predefined, and so the motion is fine.
Does it actually find for the spot it goes kind of the normal in that spot?
Yeah.
It could drill in?
Yes.
Okay.
Does it include the, not the,
Yeah. It's supposed to be. It's not supposed to, it's. Two pence. Yeah. Okay.
yeah, but we have defined as a normal.
Yeah.
The surgical plan. I don't know.
Are we ready to go?
We are ready to go.
This is not cutting. Yeah.
Okay, ready to go?
Yeah.
Okay, we're ready. Do you want to hold it on or is that something?
Absolutely.
That's why I was asking.
How much?
Yeah, go ahead.
Yeah.
What's that?
Yeah, annotate.
Yeah.
So annotate.
Okay, so let's same thing.
Look at this automatic things. While it's still, it's all this like updates.
Well, that's the motion planner, yeah, the part, yeah. That's the,
Yeah.
But yeah, the key thing is the right thing. Where is it? Essentially.
So, all right, there. Things start with it. Okay, so same workflow. Track first, goes there. Give it a moment to register. I think it's just fine. And then, well, the most important part of having this button is to well visually confirm that it looks right. So, as you can see, it looks right, which is why I'd say continue. Yeah.
So we're doing a different point. Slightly behind.
Yeah.
Yeah. Pencil on that? Is this one?
So this can be
I don't know
different,
how
we can
better to
also
put it
work
across
with
as
outside.
apart from that you can see the whole.
Yeah, it's right, is it right there? Okay, maybe a different hole, a
The
small
second
hole.
hole, yeah. We gave it the new goal with the flip location. And this is the second hole. And this. So if I mount the stencil on here, you can see the hole from this.
Yeah, like a millimeter on the side.
Yeah.
We've done it.
Millimeter and a half on the side.
Yeah. Yeah.
Pretty good. And
Yeah, so I think that answers Shivani's question that we can flip the bone completely and still get 2 mm accuracy in a random other point that we have chosen. So, we can, I think, skip over the offline results since our online results have been good as well. But yeah, that's it. Thank you and break a leg.
you have, I think we have 2 minutes left. Do you have any known failure cases? Yeah. The drill?
Yeah,
So,
it goes.
yeah, the
So-
drill,
As of yesterday night, we had, we first had a laser setup that we were doing for testing accuracy. That broke. Our drill broke. Last night we had issues communicating to the end
The
effector.
connection between the manipulator and PC also broke.
The only time that happened before this was the SVD encore. And then something else happened with the Arduino connection and everything was broken as of 2:30 a.m. last night.
made a good recovery.
Yeah.
Telling your peers from the first year. This man.
Always buy two hardware.
Gremlins also.
Always keep two hardware.
Good, okay, what else?
This flex shaft broke. Like we didn't even imagine that that could be a failure case in the entire system. We thought like, okay, the drill bits might break, end effector could break, motor could start malfunctioning, but no one even thought that, hey, the flex shaft might just stop this disconnect. So, yeah.
The last week has been very good.
But if all that goes right,
Yeah.
are there cases where you don't get the hole quite accurately enough?
So,
I think because you've tuned the offset of calibration and everything for the current height, that's why we go to the track post and then we do it. It's very good. But if you were to register at a higher height, if the workout is noisier, it will help.
there's like
And
a,
there are.
Enough, it's down further.
Oh, yeah.
The flexion, that
Actually, the resistance is poorer, relatively, because it has a curve as part of the thing and that.
so now they're passing wrong.
Should we pass it around?
Like, so basically,
Yeah.
basically when you're in this flexion, these points are not visible to the camera. But that's
So have you done any significant misses? So, yeah.
basically,
Maybe we're running out of time. Yeah, okay. So sometimes we can go up. We do go up, yeah.
So-
Infinite of goals is better than I see.
so the situation that happens is if the orientation is too much straight, aligned with the end vector,
Oh, I see.
which is not a situation that you would actually occur in a procedure, but yeah.
In
like-
relation to the operator.
Yeah, so if you were like this, it will probably have a lot. This will have a lot. I can say that.
Which can you feel complete?
We keep that for answer.
Is that someone here? Good. Okay, congratulations.